Okay, so hello everyone again. This is lecture number 7 of motion in a plane. In the previous discussion, we were talking about, we started talking about projectile motion, in which we studied different aspects of projectile motion. Let us start with the further discussion on that topic only, and then we can move forward. So, this is lecture number 7 of motion in a plane. I'm Samir Lawankar. Let's begin our discussion. So right now we are on the 10th topic, that is projectile motion. Okay. So before that, let me do a quick recap of everything which we have studied till now, and then we can move forward. Okay. So I think today a detailed recap is required so that we can understand each and everything, and we can start remembering also as we move forward. Okay. So introduction. So first of all, in introduction, we understood as in what was the difference between the motion in a straight line and motion in a plane. Okay, so we understood that motion in a straight line is basically in, let us say, x direction, or let us say in y direction, or let us say in z direction. Correct? What happened in motion in a plane? We basically started working in a xy axis. Correct? So let's say xy axis, or yz axis, or zx axis. Okay, fine. Next thing which we understood was about scalars and vectors. Okay, so if I make a division between scalars and vectors, what can I say? I can say simply that scalar is something which has a magnitude, and it has a magnitude plus direction. Okay, then next thing was based upon here algebraic operations can be obtained, so algebraic expressions can be directly applied. Here it cannot be applied. Okay, next thing was example of this. So example can be, let's say, path length, then time, then temperature. What can be examples of vectors? Velocity, displacement, acceleration, etc. So that was the basic division of your scalars and vectors. Then in next thing we started understanding the properties of vectors, in which one of the property was multiplication of vector by a real number. The next thing we understood was addition and subtraction of vectors, as in, let us say, if this is some vector A and this is some vector B, then A plus B is basically this. Okay, next thing is P bar is nothing but equal to A bar minus B bar, which is also equal to A bar plus minus B. So what we'll basically do, let us say this is B bar, you'll just reverse the direction and you will add A into it. And that is how we can do the subtraction of vectors. Okay. The next thing was about resolution of vectors. So basically what does resolution tells you about? The resolution of vectors simply states that, let us suppose there is some vector A. There is some vector small a. There is some vector small b. So it simply states that the vector capital A can be written as the summation of this A and B with some factor multiplied into it. And this is nothing but, we can say that the capital vector A is being resolved into two different component vectors, small a bar and small b bar, in the terms of lambda a bar and mu b bar. Okay. In the similar case scenario, you obtained the same results in the terms of your coordinate axis. Let us say we are working with xy axis. Then we said that there is a unit vector in this direction with I cap, and there's a unit vector in this direction with j cap, and there's a vector being drawn here like this. And if you draw perpendicular from this and this location, we can obtain this length as equal to ax and this as equal to ay, and therefore we can say that a bar is nothing but equal to ax I cap plus ay j cap. That was the complete brief detailing of resolution of vectors. And the next thing, we understood the vector addition, that is analytical method, in which we basically derived the formula, which is r is equal to under root of a square plus b square plus 2ab cos theta. Correct? Where also tan theta is basically equal to your b sine theta. That is how we derive these results, as in what is the resultant vector r with respect to, if this is a, this is b, this is theta, and this is alpha. So we can obtain everything if, let us suppose, we have the value of a, b, and theta. So this is also called as your law of cosines. Okay, fine. Then we started understanding the motion in a plane, and finally understood motion in a plane with constant acceleration, in which again we derived the vector or the kinematics equation in vector form. The first was v is equal to v naught plus at. The second was r is equal to r naught plus v naught t plus half at square, and the final was v square is nothing but equal to v naught square plus 2a into r minus r. Okay, so these are the three kinematics equation. Finally, we understood the relative velocity two dimension, which was same only, just the interpretation now will be in 2D plane. So velocity AB is equal to VA minus VP, and similarly velocity BA will be equal to velocity V minus velocity A, and also velocity AB is equal to minus velocity B. Okay, fine. So right now we started with the projectile motion in the previous lecture only, in which we were able to understand, first of all we understood what is the equation of path of projectile. Then second thing was we understood what is the time of flight and time of maximum height, and then we understood maximum height. Okay, so please remember all these formulas, because these the questions are directly asked using these formulas in the exam. Okay, so that being said, let us start with this discussion, and then let us understand the range, and then we can move forward. So projectile motion. So these all things are already understood. So we finally found that what was acceleration here. Acceleration in this case scenario is equal to minus gj bar. Okay, then we found that the velocity can be resolved into two components, that is v naught cos theta naught and v naught sin theta naught. Then next thing we got that we assumed the initial displacement to be zero in both these cases. Therefore, this was the way in which we got the displacement values, correct? Then next thing was velocity in x can be assumed as v naught cos theta naught. As you can see, it is quite independent of the time t, and velocity vy is equal to v naught sin theta naught minus gt. Okay, then anything else? This was the path. In the further discussions, we found that the equation of path of projectile is this, which is y is equal to tan theta naught x minus g by 2 v naught cos theta naught whole square into x square. As this and this can be said as constant value, because we know that g is constant, v naught will be constant for a projectile, and cos theta naught will also be constant. Therefore, cos theta naught and tan theta naught are constant. Hence, this can be written in the form y is equal to ax plus bx square, where a and b are constants. And you will get to know further in the mathematics classes that this is nothing but the equation of a parabola. Okay, that is the path of projectile is a parabola. That thing being said, we went on to understand the time of maximum height, that is equal to v naught sin theta naught by g, and finally derived the time of flight, which is 2 into v naught sin theta naught by g. So this is known as time of flight of the projectile. And the final discussion was that the maximum height hm required for the projectile can be calculated by putting t is equal to tm in this equation, that is for displacement of y, and therefore we got that the maximum height of the projectile is equal to v naught sin theta naught whole squared upon 2g. Okay, Try to derive all these scenarios by yourself without looking at any of the formulas. If you're able to derive, it is quite easy to understand the complete concept we are trying to understand here in project animation. Okay. Fine. So that thing being said, now let us try to understand today's discussion. The first discussion that we are trying to understand is based upon the horizontal range of a projectile. Okay. So what we are basically trying to find it out here, we are trying to find out this value. Okay. Let us try to find out. So the horizontal distance traveled by a projectile from its initial position, that is this x is equal to 0, y is equal to 0, to the position where it passes y is equal to 0 during its fall. So this position is called as the horizontal range. So because it is in horizontal form, it is also called as horizontal range. Okay. It is the distance traveled during the time of flight tf, quite evident. So there will be movement in this form like this, and finally you will reach here. So you basically need to find out the velocity. Find out the displacement at some time tf. How it can be obtained? We know that the displacement x is nothing but equal to v naught cos theta naught into time. So at t is equal to capital Tf, x is equal to r. Correct? So when t is equal to Tf, x will be equal to r, because that is the complete time required. Just put the values, you will get r is equal to v naught cos theta naught into 2v naught sin theta naught by g. This expression can be written as r is equal to v naught by g, v naught whole square by g, because there are 2 v naught, into 2 sin theta naught cos theta naught. Again, you will referring you to the mathematics lectures, you will understand in trigonometry again in this class 11th only, that r is nothing but so this is v naught square by g only. This can be written as sin 2 theta. Sin 2 theta. Okay, so sin 2 theta is nothing but equal to 2 sin theta cos theta. Okay, so that thing being said, we got the range as equal to v naught square sin theta by g. Okay, so that is the derivation being done for range. So therefore r is equal to v naught square sin 2 theta naught by g. Okay, now above equation shows that for a given projection velocity v naught. Okay, so depending on the velocity v naught and sin 2 theta naught, the value of range may vary. Now when is this r maximum? If you see clearly to the formula we obtained for range, it's v naught square by g into sin 2 theta naught. Okay, so we know that what is the maximum value which this can obtain, because v naught and sin theta g are same only. The maximum value which this can obtain is 1. So when this will be 1, we will get the maximum value of range. So r is maximum when sin 2 theta naught is maximum. That is when theta is 45. So try to put theta is equal to 45 here. You will get 2 into 45, which is equal to sin 90, which is equal to 1. Correct? So therefore the maximum horizontal range which is obtained is equal to v naught square by g. Okay? So therefore from this slide here, first of all we got r is equal to v naught square sin 2 theta naught by g, and then we also got r max is equal to v naught square by g. When it is obtained when theta naught is 45. Okay, fine. Now let us try to understand another it is a further discussion of range only, but we are trying to understand it using an example. Okay, so Galileo in his book Two New Sciences stated that for elevations which exceed or fall short by 45 degrees by equal amounts, the ranges are equal. What does it try to say? I will try to explain it using a diagram here. Let us suppose this is your xy axis, correct? And this is your 45 degrees. This is your 45 degrees. Now they are saying is, so the maximum range which will be obtained would be for this value. Okay, so the diagram may not be completely correct. You can just analyze it using a parabola. What they're saying is, let us say I deflect it to it somewhere like this. Let's say this to be angle theta. And similarly, I deflect it again here. So these are different velocities. Okay, so these are different projectiles. One we try to shoot it at this projectile. Another time we try to shoot it at this projectile, and another time we try to shoot it at this projectile. So they are just saying that let us suppose that this also be angle theta. So angle 102. So 102 is basically 102 is equal to theta, and similarly angle 103 is also angle theta. So if we try to deflect from 45 degree by the same proportion or by the same angle, then the amount of range it gets is same. This is the thing which we need to prove. Okay, you can see from the figure also that the maximum is being obtained for 1, but the 2 or 3 are minimum, but because the angle of deflection is same, it is the ranges for both are same. So we are just trying to prove this here. Let us try to prove. So for the projectile launched with a velocity v0 and angle theta naught, what we know, what is the value of range? Range is nothing but equal to v0 square by g into sine 2 theta naught. Okay. Now for angles 45 degree plus alpha and 45 degree minus alpha, 2 theta naught is 90 degree plus 2 alpha and 90 degree minus 2 alpha. Quite evident, because what we were basically doing there for the above part, let us say if this is 45 degree, what will be the angle of inclination for the above one? It will be 45 degree plus some theta. Correct. They are just using this theta as alpha here. Okay. So this is basically alpha here. And similarly, if you are doing it somewhere downwards, so what will be the angle of inclination this side? It is 45 degree minus alpha. So they are just saying that if theta naught is 45 degree plus alpha, 2 theta naught will be 90 degrees plus 2 alpha. Similarly, if theta naught is 45 degree minus alpha, 2 theta naught is 90 degrees minus 2 alpha. Okay. So therefore for angles 45 degree plus alpha and 45 degree minus alpha, 2 theta naught becomes these values. And now the values of sine of this and sine of this are the same, equal to cos 1. Okay, so if you just, again, it's a mathematical trigonometric identity, so I won't go into expression of this. So this will be using the formula sine a plus b and sine a minus b. So sine a plus b, sine a cos b plus cos a sine b. So using these formulas, you will finally obtain that sine of, so these all mathematical entities will be understood to you in the mathematics chapter. Okay, so sine 90 degrees plus 2 alpha will give you cos 2 alpha, and sine 90 degrees minus 2 alpha will give you cos 2 alpha. Okay, so therefore the ranges are equal for elevations which exceed or fall short by equal amounts. So you can see clearly that as this is both cos alpha, what you will get finally, you will get range is nothing but equal to v0 square by g into cos 2 alpha. Okay, so this is the alpha which is here. This is the alpha being talked about here. Okay, so that was how we understood this concept also. So this is also a discussion about your range. Okay, fine. That thing being said, let's move forward. Another example now. Okay, so a hiker stands on the edge of a cliff. What is a cliff basically? This is an example of a cliff. So this is a cliff. So a hiker is standing here. Let us suppose he's standing here. Okay, on the edge of the cliff, which is 490 meters above the ground. So this is basically 490 meters. Okay, so this is basically 490 meters above the ground. And let us suppose this is the ground. Okay, and it throws a stone horizontally with an initial speed of 15 meters per second. So let us suppose there was a stone here and it was being thrown like this. Please remember, it is not being thrown at an inclination. It means the inclination is 0 here. But this was how the stone was being thrown. Okay, so what would be the path? The path would be something like this. Okay. Neglecting air resistance be neglected. We just need to find the time taken by the stone to reach the ground. Okay, we just need to find the time required with the stone to reach the ground. and the speed with which it hits the ground, and the speed which it hits the ground. So basically, we need to calculate the velocity at this location here, and next thing is the time required. Okay, so let us just derive using this concepts of your projectile motion. We can refer to this question. Only this time the velocity is in x direction and with inclination 0. Okay, so we choose the origin of x and y axis at the edge of the cliff at t is equal to 0 seconds at the instant a stone is thrown. So let us take the origin to be at this location here, and we are throwing it somewhere like this. Okay, now choose the positive direction of x-axis to be along the initial velocity and the positive direction of y-axis to be vertically upward direction. So that is how we are choosing it. Correct? Then x and y components of the motion can be treated independently. Okay, so therefore the equation of motion becomes what? You know, x, that is displacement, is nothing but equal to x naught plus v naught xt plus half ax t square. Therefore x becomes, we know initial displacement x naught plus v naught x will be 15 this time into t plus ax is 0. This is the first equation we obtain. Similarly, for the y term, what we can say? Y is equal to y naught plus v naught yt plus half ay t square. Correct? So here y is nothing but equal to again 0 plus 0, because velocity in y direction this time is 0, plus half into minus g into t square. Okay, so these are two relations being obtained. The similar thing which I am doing here, we know x naught y naught is 0, velocity in y direction is 0, acceleration can be taken as minus g, that is minus 9.8 meter per second square in the y direction, and v0x is 50. So just put everything here. What will you get from this relation? You can get x is equal to 0 plus 15 into t, and from second relation we can get y is equal to minus half g t square. Correct? So we need to find out when does the stone hit the ground. So time required for stone to hit the ground. So because the displacement in the negative direction is 490 meters, so therefore in the place of y we can put 490 in the y direction. Please remember, because the displacement is in downwards, therefore we will put minus 490 there and not plus 490. Okay, so therefore when you will calculate, you will get t is nothing but equal to 10 seconds. So we found the first thing, that is the time required for the stone to reach the ground. Fine. Moving forward, now using the equation for the components of velocity. So here, because there is no acceleration in the x direction, the velocity in x direction will be same only. That is vx is equal to v naught x. What will be vy? Vy will be vy minus gt. As we need to know the time at 10 seconds, it will be equal to 0 minus 9.8 into 10, which will give you minus 98 meter per second. This will be plus 15 meter per second. So you know the value of vx, you know the value of vy. Just put it here and you can get the speed, which is under root of vx square plus vy square, which is equal to under root of 15 square plus 19 square. Okay, so that's how you obtain the speed also and the time. Okay, fine. Again, a question on projectile motion only. So let us try to understand the question first and then we can move forward. Okay. So a cricket ball is thrown at a speed of 28 meter per second in a direction 30 degree above the horizontal. Okay. So what is the situation here? So let us say this is a cricket ball and it is being thrown at 28 meter per second. That means this velocity is given to u as 28 meter per second and direction is given to u as 30 degrees. Okay. Calculate the time maximum height. First of all, let us calculate the maximum height. We know the formula. What is maximum height formula? It is nothing but equal to v naught sine theta naught whole squared upon 2g. Just put the values. It's 28 into sine 30 degrees whole squared upon 2 into 9.8. Just do the calculations. You will get the answer as equal to 10 meters. Okay. Simple mathematical formulation, simple value putting, you will get the answer as far as you remember the formula. Okay. Second question says that what is the time taken by the ball to return to the same level? If it is being asked that the time required to return to the same level, that means they're talking about a total time of flight. Again, simple formula usage only. So we know what is TF. TF is nothing but 2 into V naught sine theta naught by G. Just put the value. So it's 2 into 28 into sine 30 degrees by 9.8. Just solve it. You will get the answer is equal to 2.96. Okay. Fine. Moving on. What is the third question being asked? The third question says that the distance from the thrower to the point where the ball returns to the same level. So if they are talking about the ball returning to the same level, they are talking about the range. Again, we know the formula for range, that is nothing but V naught square by G into sine 2 theta naught. Correct? So let's put the values again. So it's 28 squared upon 9.8 multiplied by sine of 60 degrees. Why 60? Because 2 into 30 gives you 60. Again, just put the values here. You will get the answer as equal to 69 meters. Okay. So that's how you can solve for maximum height, time taken by the ball to return to the same level, and the distance from the thrower to the point where the ball returns to the same level. Okay. So that thing being said, that is the complete example here. So we understood projectile motion also, in which we understood equation, time, maximum height, time required for maximum height, time of flight, and range. And then we solved some questions regarding this. Right. So let's move forward. So as we are studying physics, there are many assumptions which we take in each and every scenario. If you remember correctly, even in the questions also, it is written that neglecting air resistance. Okay, so why do we take neglecting air resistance into consideration? Let us try to understand. A little off the topic, but let us try to understand, as we are physicists and we are trying to understand physics at a greater level, at a deeper level. Okay, so neglecting air resistance, what does the assumption really mean? So while treating the topic of a projectile motion, we have stated that we assume that the air resistance has no effect. So what is the assumption being made? We assume that the air resistance has no effect on the motion of the projectile. You must understand what the statement really means. So friction, that is friction. So these are examples. Okay. So friction, force due to viscosity, and air resistance are all dissipative forces. So a new word has arrived here, dissipative forces. Please understand, dissipative forces are forces which lead to loss in energy as the path or motion occurs. Okay, so this is basically a general definition of dissipative forces. That is the forces which lead to loss in energy. So friction, force due to viscosity, air resistance, all these are nothing but examples which lead to your dissipative forces. Okay? Fine. So in the presence of any of such forces opposing motion, any object will lose some part of its initial energy and consequently momentum too. Okay, so you know what is momentum basically? It is mass multiplied by velocity. This is nothing but your momentum. So what they're saying is that if such forces exist, if such forces are existing, and because they are opposing forces, opposite to the forces, let us say if we are moving in this direction, then generally these forces are in opposite direction. Okay. So in the presence of any of such forces opposing motion, any object will lose some part of its initial energy and consequently momentum too. So if it is decreasing its energy, it will decrease the momentum too. Thus, a projectile that traverses a parabolic path, would certainly show deviations from its idealized trajectory. So this is an idealized trajectory, correct? So if there would have been a dissipative force, the amount of energy which is required here may change. There will be loss. So there would have occurred a situation in which this would have gone in, let's say, this fashion, or let's say in this fashion, depending upon the resistive force which is acting upon it. Okay, so it will not hit the ground with the same speed. So it will not hit the ground with the same speed with which it was projected from. Okay. In the absence of air resistance, the x component of the velocity remains constant. So when there is no resistance being acted, so first of all, it will not hit the ground the same field it was projected from it. So what the general understanding? Let us say these are the points at which the projectile has been taking place. So the velocity with which it was being occurred, and when it tries to reach this position, the velocity is same. But if there would have been an air resistance acting in the complete path, then the velocity wouldn't be equal to its initial velocity when it hits the ground, or the speed won't be same. The direction may change, but the speed won't be same. Okay. So because after this, the direction of velocity of Vy would change with this direction, correct? So the direction would be changed, but the speed may not be same. Okay. So in the absence of air resistance, the x component of the velocity remains constant, and it is only the y component that undergoes a continuous change. Okay, so what they're saying, that let us say there is no air resistance, and the x component of the velocity remains constant, which we have derived also previously, right? That the velocity was nothing but depending on the velocity was constant. Okay, which was equal to v naught cos theta naught. Okay, and it is only the y component that undergoes a continuous change. So because of the acceleration which was happening, that is minus half at t square, in the y displacement part, we got to know that there was a value of minus gt in the y component velocity, and hence it was completely changing as long as there is an absence of the air resistance. Okay. However, what will happen in the presence of air resistance? Both these would get affected. And if this would get affected, then the path will also change. If path will change, the time will change. If time will change, or not relation with that, if the velocity will change, there will be effect on the height, the range, the time. Okay. So that would mean that the range would be less than the one obtained before. Quite evident, because the energy is being reduced correctly. So the energy is reduced. If this was the ideal trajectory, then let us say this may be the trajectory with the air resistance. Okay. Maximum height attained would also be less than that predicted before. As you can see, the maximum height is also reduced. Can you then anticipate the change in time of flight? Okay, so time of flight will also reduce. Time of flight will also change. Okay, in order to avoid air resistance, we will have to perform. So we need to see that what will be the effect on time of flight depending upon the equation which is formed. Okay, so next thing is, in order to avoid air resistance, because how the air resistance force factor will come into the calculation of time of flight would have to be seen, and then we can say that it will increase or decrease. Okay. So in order to avoid air resistance, we have to perform the experiment in vacuum or under low pressure, which is not easy. Quite aware, it is not easy. So therefore, when we use a phrase like neglect air resistance, we simply imply that the change in parameters such as range, height, etc. is much smaller than their values without air resistance. This is the only phase, or this is the only meaning of air resistance. Okay, so when we use a phrase like neglecting air resistance, we imply that the change in parameters. So what are the changing parameters? The changing parameters are basically like range, height, etc. is much smaller than their values without air resistance. So the change is very, very less. Change in range is very, very less. Change in height is very, very less. That is, there is very minimal effect of air resistance if there would have been any air. Okay. The calculation without air resistance is much simpler than with that of air resistance. Quite evident, because actual value of air resistance, there are certain scenarios also where the pressure, so air resistance depends on pressure correctly. So we also had the pressure may change with the scenarios, pressure may change with the position of the object also. So it is quite difficult to take air resistance into scenario. The complexity of the calculation will increase. To decrease that complexity, what we do, we neglect the air resistance. So that is the basic reason of neglecting the air resistance. Okay. Fine. So that thing being said, that is the end of all the concepts till now. So we started with vectors, and then finally right now we have completed everything and we are done till projectile motion. Okay, so I suggest you to do the complete derivation of projectile motion. You can start from the basics of first of all drawing everything and understanding. Then okay, so there is some velocity which is happening. Let us say this is in this velocity in this direction. Let's say this is v naught. Therefore, I can derive it into resolve it into two components, namely v naught cos theta naught and v naught sin theta naught. Correct? Then I can derive it. So first of all, the derivation would be for x and y. How we can derive it? It is nothing but equal to x naught plus v naught t in x direction plus half ax t square, which will leave us to v naught cos theta naught t. Correct? Similarly, this will be 0 plus v naught sin theta naught t minus half gt square. Right? After this, what can be obtained? Then we can obtain the velocity in vx, which is nothing but velocity in x direction plus ext, which is equal to v naught cos theta naught only. Similarly, vy can be obtained as vyx plus ayt, which is equal to v naught sin theta naught minus gt. Right? So we know the equation for x and y also and vx and vy also. Then we can directly obtain, as in if we need to calculate the time of complete time of height, or small time, that is tm, we can just equate it to 0, and hence we can find that equal to v naught sin theta naught by g. Correct? We know if we put the value of y equal to 0 here, we can obtain the value of capital TF, which is equal to 2 v naught sin theta naught by g. Right? Then how to calculate the value of hm? If we put the value of t is equal to tm here, we can obtain the value of hm, which is nothing but equal to v naught sin theta naught whole squared by 2g. Okay? And how to obtain the value of range? In this first expression, if you put the value of t is equal to capital TF, we obtain the range is nothing but equal to v naught square by g into sine 2 theta naught. Okay. So that is how I derived it again. So everything which we have studied in the last lecture, in this lecture and the previous lecture, is being derived in front of you again. So this is how you can do the revision again and again, and this will increase your conceptual clarity regarding these all kinematic equations and kinematic concepts. Okay. Please remember, in the complete understanding of a uniform in your projectile motion, we always understood the acceleration as a constant acceleration. Okay. So in the x direction, it was 0, and the y direction, it was constant, which is equal to minus g. Okay. So that thing being said, let us move on to the final discussion regarding the motion in a plane chapter, that is regarding your uniform circular motion. So what can you understand from that words written here? First of all, motion. So motion is basically the position, the traversing of a particle from point A to point B is basically motion. If that motion is in circular sense, then this is called as circular motion. And if the amount of displacement occurring is equal in equal intervals of time, then this is called as uniform. Okay, so uniform circular motion, that is a motion of a particle in your circular sense such that the displacement is always same in equal intervals of time, and that motion is called as uniform circular motion. That is how you can understand the wordings here. Now let us try to understand the concept regarding this chapter, regarding this subtopic. So let us start a new subtopic, that is uniform circular motion. Okay. Let me iterate first of all. So when an object follows a circular path at a constant speed, the motion of the object is called as uniform circular motion. Okay, I can iterate again. So when the object is following a circular path at a constant speed, you can refer here. The object is at a constant speed. Why it is written as constant speed, you must say? Because okay, so this thing will be understood in subsequent slides only. So because I do not want to create confusion here. Let us understand it as fact right now, and we can understand it later. Okay. So when an object follows a circular path at a constant speed, the motion of the object is called as uniform circular motion. Okay, so you can understand this quite clearly. So when an object follows a circular path at a constant speed, the motion of the object is called as uniform circular motion. Fine. That thing being said, the word uniform refers to the speed which is uniform or constant throughout the motion. So because the velocity was constant, it is also called as uniform circular motion. So what is basically velocity? We know it is delta x by delta t. Correct? So if it is constant, that means that delta x is some times of delta t. So basically delta x is always constant for a delta t. Okay? For a constant value of delta t also, delta x will be constant, and hence it is called as uniform. Okay? Let's say x2 minus x1 is equal to k times delta t, and similarly some x3 minus x2 will also be equal to k times delta t. So hence you can say that it is uniform, or we can say that the displacement is c, as long as the time interval is c. Okay. So suppose an object is moving with uniform speed v in a circle of radius r, as shown in the figure. Now just keep your eyes on the figure, because now we are trying to understand, or we are trying to derive the acceleration regarding uniform circular motion. Okay. So suppose an object is moving with uniform speed v in a circle of radius r, as shown in the figure. So if you look clearly here, you can see that this was your B, this was your C, that is the center. Now if you remember correctly, I explained you the position vector. What is the position vector? Position vector is the vector drawn from the origin to the vector position at some time t. This is basically your position vector. Now the velocity at that vector is in this direction. We do it like this. Okay. So therefore, I explained you. So suppose an object is moving with uniform speed v in a circle of radius r, as shown in the figure. Now, since the velocity of the object is changing continuously in direction, the object undergoes acceleration. Okay. So basically, how to explain this? Okay. So we know acceleration is nothing but equal to delta v upon delta t. Correct? So how will acceleration change? If there's a change in the velocity, there will be change in the acceleration. Correct? Now velocity can be changed in two different ways. The first way is if there's a change in magnitude, and second thing is when there's a change in direction. So one thing is when there's a change in magnitude, and second thing is when there's a change in direction. Okay, so if there's a change in magnitude, so that thing is quite clear. But sometimes what we understand is if there is change in direction, how can there be a change in acceleration? Okay, so this thing can be understood pictorially or graphically. So I will try to understand when the time comes. But for now, you just understand this as a fact that an acceleration is so basically as delta v is changing, or the velocity is, or basically not delta v is changing, the velocity is changing. Because the velocity is changing and there is a relation between acceleration and delta v, that is why the acceleration is happening in this complete uniform circular motion. Okay. So therefore, this acceleration will have a value. We will just try to derive this value. Okay. So suppose an object is moving with uniform speed v in a circle of radius r, as shown in the figure. Since the velocity of the object is changing continuously in direction, the object undergoes acceleration. Clear? Let us find the magnitude and the direction of this acceleration. So let us try to find out the magnitude also and direction also. This finding out the direction is very, very important because this requires a little bit of detailing. Okay, fine. So let us move forward. Okay. So please understand this clearly so that you can understand how we calculate the acceleration value. This is the direction and the magnitude of. Okay. So let small r and small r dash, so these are basically vectors, be the position vector. So just a quick revision again for the vector part. So what are the different types of vectors we learned in the previous complete chapter? We started with the position vector. The second was your displacement vector. The third is your zero vector, and fourth is the unit vector. Okay, so what was basically a position vector? The position vector can be understood like this. Let us suppose this is some x and y axis, and this is some vector. Sorry, and let us suppose this is some position p of a particle at some time t, and the vector drawn from the origin O to the particle p is nothing but called as your position vector. Okay. So similarly for P dash, let's say it is the position of the particle at some time T dash. Then what will be the position vector of P dash? Again from origin O, we will draw a vector to the point P dash. So this can be written as R dash. Okay. Now if I need to ask you that what is the displacement vector for this particle? The displacement vector for this particle, let's say we talk about PP dash, will be equal to this vector here. Okay, so there is nothing but we can write it as d bar. Okay, what is zero vector? Zero vector has a magnitude which is equal to 0. The direction is not specified. The direction is there, but the direction is not specified. Okay, next thing is about unit vectors. What is about unit vectors? Okay, the magnitude of the unit vectors is equal to 1. And the direction is again depending upon the direction which you take. The examples of unit vectors are I cap, j cap, and k cap. So basically, I cap is in x direction, j cap is in y direction, and k cap is in z direction. Okay. So that thing being said, now let us understand whatever is written here. Okay. So let R and R cap be the position vectors of the point P and P dash. It is quite clear. This was P, this was P dash. Therefore, the vector drawn from the center location O to that vector P is basically position vector. Similarly, the vector drawn from this location O to this P dash, this P dash is basically R dash. Okay. So let R and R dash be the position vectors, and V and B dash be the velocities of the objects at the point P and P dash. Okay, so you can see clearly this is the velocity which is occurring here, and similarly this is the velocity which is occurring. Okay, I hope it is clear. Achha, why are the direction of velocity only in this way? This can be observed like this. So see, this is the path of the circular motion, correct? If we need to calculate the velocity at this location, we understood when we were trying to understand the subtopic motion in a plane that the velocity, instantaneous velocity, is tangent to the slope at the point P. Okay. Similarly, here also the velocity V dash is tangent to the slope of the particle, or basically it is tangent at the point P dash. So that is why the direction is in this scenario. Okay, so you may you may have a confusion as in why this is only the case. This is only the case because we have understood this topic in the motion in a plane subtopic. Okay, so let R and R dash be the position vectors and V and V dash be the velocities of the objects when it is at point P and P dash as shown in the figure A. Now, by definition, the velocity at a point is along the tangent at that point in the direction only. So everything which I just uttered is being written here. So by definition, velocity at a point is nothing but along the tangent at that point. So it is along the tangent. Here also it is along the tangent. So the velocity vectors V and V dash are as shown in the figure A1. So this is how you can see that this is velocity V and this is velocity V dash. Now delta V is obtained in figure A2. Okay, so how it is obtained? Let us look here. So there was some velocity V which was some sort of in this scenario, and similarly there was some velocity V dash which was somewhere in this scenario. Correct? Now what is basically delta V? We know what is delta V. Final minus initial, so it's V dash minus V. Correct? So if we need to calculate this V dash minus V, how can we calculate it? It is equal to V dash plus minus V, right? So just have to put it here. So this will be nothing but this is your V dash, correct? Minus V can be written like this. So this is your minus v, and I just rotated it here. Therefore, what will be the direction? The direction of the delta v will be in this case scenario like this. Okay, let me try to derive it again so that you are quite clear as in why was there a need, why we understood this complete graphical method of addition and subtraction. Okay, so basically what is delta v? You know, delta v is nothing but v dash minus v. Okay, so as it can be seen clearly, v has a direction like this and v dash has a direction like this. Okay, what we basically need to do, we need to do v dash plus minus v. Okay, so just change the scenario of v, this will be direction. Now we just need to add both of them. Okay, so if we need to add both of them, this is your v dash, correct, and this is your v. So this is your v dash, this is your v. What will be the complete resultant? The resultant will be this r, which is nothing but equal to v dash minus v. And that is how we obtain the direction of delta v to be in this scenario. Okay, so I hope you understood how we obtain delta v to be in this direction. Okay, fine. So therefore, delta v is obtained in figure A2 using a triangle law of vector addition. So that is how we understood this complete concept of triangle law of vector addition. So basically, one of the example of triangle law of vector addition. Okay. Next thing is, since the path is circular, we know that the path is circular like this. Since the path is circular, v is perpendicular to r. V is perpendicular to r. So this is perpendicular to r like this. Okay. And so is v dash. So v dash is also perpendicular to r. This is quite evident because it is circular motion. Okay. Therefore, delta v is perpendicular to delta r. Right? Because we know delta v is nothing but equal to v dash minus v. Right? Because these are perpendicular to their respective operations, delta v will be proportional to delta v will be perpendicular to delta r operation. Okay. Therefore, since average acceleration is along delta v dash, the average acceleration a bar will be perpendicular to delta. So now because delta v can be written as delta a bar, which is equal to del v by del t, therefore we can say that average acceleration a has a direction which is perpendicular to delta r. So this is the direction of delta r, and hence the variation or the variation in which the a will occur or a bar will occur will be in this case scenario. So because delta r is in this form here, as you can see, it is perpendicular to it, and this is the direction of a. Okay. So that thing being said, let me end this lecture here. So this was a basic idea of how we understood the concept of a bar. Now we'll try to decrease this delta r value and obtain the instantaneous value of acceleration. Okay. So let me stop this lecture here only. We will move forward regarding this in the next chapter.